Hello everyone, welcome back to our YouTube channel. Today is the third day of our Verilog series, and the topic of the day is Verilog structure and syntax. Without further ado, let's start. Before we dive deep into what is the syntax, I want you to give a reference about how does the overall architecture of any design that we'll be making in Verilog will look like. Each and every Verilog design is made up of building blocks called module. Whatever logic that you will be writing will come inside the module block. We will take a look into how does a module block looks, what is the syntax of module block in the further slides. Before that, I also want you all to get an idea about test bench. Test bench is also a type of module which will be used to apply inputs to a design module. Broadly, we can classify any module, all the modules in two parts. Modules which are implementing some kind of design, and there are test benches which are used to verify those design modules. Overall architecture looks something like this. We have a test bench. In the test bench, there is some logic written to generate clock, as most of the modern circuit work synchronously with the clock. For those designs, the clock will be generated in the test bench. Then there will be some input stimulus generated via test bench that will be provided to our design module. The module can be of anything: RAM, FIFO, even any protocol design such as I2C or SPI. We already discussed in the previous videos that what are all the places that Verilog can be used. Hence, any design that is being made by Verilog can be such a DUT. DUT is nothing but design under test. And once the varied inputs are provided to any design, then all the outputs can also be observed via test bench. This was a high level architecture of how of any design that we are making in Verilog and test bench that we are making to verify those designs will look like. Now let's take a look at the syntax. Verilog module syntax. As you can look here, to declare any module in Verilog, we need to use the module keyword, which is indicated here. Once we write the module keyword, after that, we need to specify a module name. There are certain rules for naming any module. We will be taking a look into that in the next videos. Those rules apply similar for the module name or any variable name as well. Now, once we have used the keyword module, declared the module name, the most important thing here, then we need to decide how many inputs or output ports will be there. Here we are taking four ports: A, B, Y, and Z. Now, I am declaring port A and B as input port, while port Y and Z as output port. Here we can also declare that AB as input port in this bracket also, and output Y and Z here. There are two methods to declare a port as input or output, whether to declare it inside the module or while we're defining the module. Both the choices are valid. Once we have decided how many ports we are going to be using, then there will be some internal logic which we can write after the port declaration. Once all the logic has been written, the end module keyword is used to indicate that this block of module is completed. Now let's take a look at example. How would this look like in a practical code? Here I have a very simple module name adder. I declare the module adder with three ports: A, B, and sum. Now I declare ports A and B as input port. Here it is written that we are declaring A and B as 4-bit port, 3 down to 0. No need to be confused right now that what does 3 down to 0 mean or why are we writing it like this. We will be going over this in the further videos. For now, I just want you all to get an overall idea about how does a module looks like in Verilog. As we discussed earlier, the first step was to declare a module name with module keyword and provide the list of ports that we are going to be using. Then declaring the direction of the ports. whether they are input ports or their output. Input ports will receive the data from an outside module or a test bench, while the output port will be used by the module to provide data to the outside world. Once we have declared the module, then I have written a logic assign sum is equal to a plus b. You can understand it as ultimately the input ports A and B will be added together to provide the output sum. And what does this assign keyword do? We will also be taking a look at it in detail in further videos. And once I have completed my logic, I will write AND module. So this is a basic example of adder. And how does the syntax rules which we discussed look like for a practical example? I also wanted to give you an idea about how would a test bench look like for this Verilog module. This is a sample test bench for this adder module. Right now, you will be seeing too many things which might confuse you. So I will ask you to be patient for a bit and only focus on things which I am trying to explain. As we progress with the series, you will be able to write all these test benches as well as design module on your own. As I mentioned earlier, test bench is also a form of module. So I will be writing the module keyword and providing a module name. Here you can see there are we have not defined any input or output ports. Why? If you go back and take a look at the architecture, test bench modules are just used to provide input and output to stimulus. Input stimulus to duty and observe output. And how we are doing it without an input output ports? That is by taking an instance of the adder module. This module which we have declared here is module adder. We will be taking an instance of this module in this test bench. Then we are having some local variables register A and B and a wire sum. What is register, what is wire, we will also taking look at it in the next video itself, that is data types in Verilog. So I just want to give you overall idea about this how does a test bench structure looks like. We have declared variables, then we instantiate any module which we are trying to verify. Then the input and input stimulus has been provided. And once we provide the input stimulus, then we can end this module. Now I will show you what will be the output of this here. As you can see, the inputs that I have given is decimal 1 and 2. So their sum should be 3, which we are getting correctly. And the next input that has been provided is 15 and 1. Hence, the output should be 16, which is coming correctly in binary system. So this was an overall look into how does a Verilog module looks like and what are the key syntax guidelines which we need to follow. From the next video onwards, we will be taking a look at what are the data types available in Verilog and what are various operators which you can use to define or create various kind of logic in Verilog. Thank you everyone for watching. Please comment if you have any queries. We will be happy to support you.